In this module, we will discuss supervised learning methods that can be applied to high-dimensional data. That is, when the number of covariates exceeds the number of samples, such as those arising from high-throughput genomic assays. Last week, we focused on penalized linear regression for predicting a continuous phenotype and penalized logistic regression for predicting a binary phenotype. This week, we will focus on algorithmic methods. There are two dominant cultures in predictive modeling. Statistical modeling has been the dominant culture and includes methods such as linear regression, logistic regression, linear and quadratic discriminant analysis, among others. These methods are based on mathematical theory and require that distributional assumptions be met by the data being modeled. Because data may violate underlying distributional assumptions, algorithmic modeling, sometimes called machine learning, has become popular. These are computationally intensive methods that make minimal assumptions about the data structure. Some methods were developed to more closely emulate our natural way of thinking about classifying objects or samples. In this module, an overview of Bayes' decision rule will be provided. Then linear and quadratic discriminant analysis will be introduced as a launchpad for introducing kernel discriminant analysis. Also, k-nearest neighbors, classification and regression trees, bootstrap aggregation, and random forests will be described. We will start with the goal of predicting one of k classes. Therefore, our problem is one of classification. That is, how do we classify n observations to one of the k classes? To introduce some notation for our classification task, we have n observations, and for each observation, we have p measured covariates. Our vector x sub I includes p features measured on observation I. X sub p is the pth predictor that stores measurement values for all n subjects in our data set. We typically let our data matrix, capital X, store subjects in rows and predictors in columns, which is how the phenodata object in an expression set is stored. Each observation belongs to one of the k classes, which is represented by omega. Therefore, our learning set is composed of n observations, and for each, we have the class and the p features. Our objective is to derive a function that takes the p-dimensional features and accurately outputs the class. For a classification task, each observation belongs to one of k classes, and the proportions of observations in class K are denoted using this notation, which may be known or unknown. The pth feature vector from class K has a class conditional density function denoted using this notation. A classifier is a systematic way of predicting class membership. Class membership can also be called outputs, responses, or dependent variables. So a classifier is a rule that assigns one of the k-class labels to every measurement vector, that is, for subjects I going from 1 to n. The basic purpose of a classification study can either be to produce an accurate classifier or to uncover the predictive structure of the problem. With respect to uncovering the predictive structure of the problem and trying to get an understanding of what variables or interactions of variables drive the phenomenon, that is, to give a simple characterization of the conditions in terms of the measurement variables that determine when an object is in one class rather than another. Ideally, the partition should be arranged such that none of the decisions are wrong, or at least the partition should minimize the probability of error or average cost of an error. Therefore, the primary assessment of a classifier will be by its performance. Therefore, classification is a problem in statistical decision theory. An important criterion for a good classification procedure is that it not only produces an accurate classifier within the limits of the data, but that it also provides insight and understanding into the predictive structure of the data. The other aspect of performance is power of explanation. As an aside, often the most important aspect of design is to choose the right features. Enhanced success often comes through enhanced features rather than through more complicated classifiers. The major guide used in the construction of classifiers is the concept of Bayes' rule. Let A and B be two events of the probability space. The conditional probability of A given B is given by this equation. Suppose B sub 1, B sub 2 through B sub k are mutually exclusive and exhaustive partitions of the event space omega. The theorem of total probabilities is given by this equation. Then Bayes' rule is the probability of B sub k given A, where the numerator is from the multiplication rule and the denominator is by the theorem of total probabilities. Let's look at a binary class problem illustrating Bayes' decision rule. Suppose lumber coming out of a lumber mill is either ash or birch. Let omega denote the state of nature or class, where omega equals 1 represents ash and omega equals 2 represents birch. Because the state of nature is unpredictable, we consider omega to be a random variable. Assume there is some a priori probability, the probability that omega equals 1 and the probability that omega equals 2, which reflects our prior knowledge of how likely we are to see ash or birch, respectively, before the lumber actually appears. Suppose further that you were forced to make a decision without being allowed to see the lumber, but you know the prior probabilities. What is a reasonable decision rule? Decide omega equals 1 if the probability that omega equals 1 is greater than the probability that omega equals 2. Otherwise, decide omega equals 2. If the two probabilities are equal, then we have a 50% chance of being correct. Now suppose we have more information. For each piece of lumber, we have brightness readings, and the different types of wood are known to yield different brightness readings. Consider X to be a continuous random variable whose distribution depends on the state of nature or class. Let P of X given omega equals K be the class conditional probability density function for X. That is, it is the probability density function for X given that the true class or state of nature is omega equals K. Therefore, the difference between these two class conditional density functions describes the difference in brightness readings between ash and birch. Hypothetically, suppose this figure represents the distribution brightness readings for ash and birch. Clearly, information on brightness readings would help our decision rule or classifier. Suppose we know the a priori probabilities and the class conditional densities. Suppose further that we measure the brightness of a piece of lumber and discover the value of X. Then, using Bayes' rule, we have the posterior probability given by this equation. For a piece of lumber with brightness reading X, if the posterior probability that omega equals 1 is greater than the posterior probability that omega equals 2, we would be inclined to decide that the true state of nature is omega 1, as that decision minimizes the probability of error. That is, the probability of committing an error is the posterior probability that omega equals 1 if we decide the class is 2, while the probability of committing an error is the posterior probability that omega equals 2 if we decide omega equals 1. If for every observation we make a decision to minimize the probability of error given our covariate x, then this integral will be as small as possible. The average probability of error is given by this equation. Therefore, we have Bayes' decision rule expressed here. Notice that in the formula for the posterior probability, the denominator will be the same for all k classes. Therefore, P of x is a scaling factor that can be omitted when using this posterior probability in a decision rule. That is, we could equivalently decide that omega equals 1 if the numerator for class 1 is greater than or equal to the numerator for class 2, or decide that omega equals 2 otherwise. Therefore, the kth discriminant is given by g sub k of x. Notice that if the class conditional probabilities are equal, the decision hinges on the prior probabilities. If the prior probabilities are equal, the decision hinges on the class conditional densities. Rather than assessing if the first discriminant is greater than the second discriminant, we could subtract the second discriminant from both sides such that we can compare this difference to 0. We call this difference our discriminant function, as it is simply the difference between the two class-specific discriminants. So far, we have described our classifier using one predictor variable. We may want to generalize this rule to allow the use of more than one predictor variable. To do that, we simply replace the scalar x by the vector x. Development of a prediction rule or classifier is a supervised learning process. Creation of the classifier requires a set of observations called the training set or learning set, in which the outcome to be predicted by the classifier is known. Ultimately, the accuracy of the classifier must be assessed. As was discussed in the last module, the misclassification rate can be assessed by applying the prediction rule to an independent test set or by cross-validation. The misclassification rate can then be used to judge the performance of the classifier. Ideally, the prior probabilities and the class conditional densities are known. In that case, we can construct Bayes' decision rule directly and will understand the minimum achievable error because there are no unknowns. In slide 9, the densities were Gaussian with known means and variances. These can be plugged into Bayes' decision rule for classifying a new observation.